So let's go ahead and look at acid and base strengths. So acid strength is going to be defined by basically equilibrium position. So we've already discussed equilibrium in length in chapter 15. We know that the farther to the right in equilibrium lies, the more product you've produced. The farther to the left, the more reactant remains. So in the case of strong acids, we have an equilibrium position that's really far to the right. So basically what we're saying is that all of the acid has ionized or disassociated and subsequently given you products. So in the case of strong acids, you have 100% ionization. So whatever concentration or amount of acid you start with, that's going to correspond directly to the amount of your conjugate acids and bases that you obtain. Now, what you need to understand is that strong acids actually produce weak conjugate bases. Okay, so this HA is going to produce a weak conjugate base. And what that means is that if we look at H2O versus A minus, or in that case the conjugate base, with respect to composition or competition for those protons that may be floating around in solution, the reality of it is that the H2O is going to be the one that picks up the protons before the conjugate base. So basically, strong acids give you very, very weak conjugate bases, and basically they're not going to really affect your adjustment of proton quantities in solution. So weak acids, on the other hand, have equilibrium positions that are actually far to the left, okay, so towards reactants. So that basically means that at equilibrium, if you have a weak acid, you're still going to have most of your acid in its combined form. So basically it's protonated form. Right? Now, something you need to understand is that the weaker the acid you have, the stronger the conjugate base that is produced. So whatever does ionize in the case of a weak acid, the base that gets produced is actually going to end up being stronger than the H2O. So in terms of H plus being floating around in solution, if there is in fact any added to solution or remaining, that that conjugate base is going to want to pick it up before the H2O is. And this is going to become very important when we start talking about titrations and things of that sort. So just keep this in your mind. Understand that strong acids are going to basically ionize completely and give you lots of weak conjugate base. Weak acids are going to ionize very little and give you very or rather stronger conjugate bases than their strong acid counterpart. Okay, so the takeaway, of course, is that your strength of your acid or base is directly related to its equilibrium position, so its ionization, so its ability to basically break apart and give you, your ions in solution. Okay, the easier the time it has to do this, so basically the farther to the right this equilibrium lies, the stronger your acid is going to be. Okay, same thing with bases. Now, the strength of your acid or base, guys, remember, has nothing to do with the concentration. It only has to do with this equilibrium position. So HCl is going to be a strong acid if it's in its concentrated form or even in its dilute form. Okay, it doesn't matter what you have in terms of quantity. All that matters is that equilibrium position. So HCl is going to be a strong acid regardless of your concentration. So let's go ahead and let's look at the relative strengths of basically some acids and the conjugate bases that are produced. Okay, so if you guys look at this chart here, notice we have a big list of acids. Okay, we have strong acids up here at top, a bunch of weak acids up down here at the bottom. Okay, and we have the subsequent conjugates that are produced from each of these. Okay, so I want you guys to notice, look, perchloric acid, hydrochloric acid, hydrobromic acid, HCl. Okay, these are all examples of strong acids. We know that strong acids have equilibrium constants that lie far to the right, so they ionize completely and produce relatively weak conjugate bases. Okay, so in this chart, the stronger acids are going to have weaker conjugate bases. So notice that on the chart, the base strength is decreasing, right? Okay, so if we know what the conjugate source is, right, if we can figure out that, hey, this comes from this type of strong acid, we can know that this is going to be a weak conjugate base. Okay, and the flip side of that, obviously, the weaker our acid, the stronger our base is going to be. Okay, so in case of HF, okay, the fluoride ion, okay, that's a little stronger base than what we would have seen with something that, you know, HI or HCl, something that's has a stronger acid source. Okay, H2O, when it behaves as an acid, it produces the hydroxide ion, which we know is a strong base. Okay, and the ammonia ion, okay, the ammonia molecule, we know that it's a weak base, right? But it's going to go ahead and produce this amide ion if it behaves as an acid. Okay, and so you're subsequently going to get a much stronger base. Okay, so look, stronger your acids, the weaker its conjugates. Okay, the weaker your acids, the stronger its conjugates. Okay, very straightforward. So here we have a nice little visual summary of kind of what we would have in solution depending on if we had a strong acid or a weak acid. So strong acids, before ionization, we have obviously a container of just HCl or whatever that strong acid is. Okay, at equilibrium, though, all of the HCl has ionized into H plus and Cl minus ions. Okay, you're not going to have any HCl molecules any longer. It's all just going to be your H3O plus ions, okay, your hydronium ions, okay, and we can see them kind of peppered throughout here, okay, and of course your Cl minus ions. So remember that the protons don't just float around and hang out by themselves. Okay, they actually get attached to that hydronium ion if there's some water present. Okay, so this is all you're going to have in solution when you're dealing with a strong acid because it's going to ionize 100%. In the case of a weak acid, such as HF, at equilibrium, you're going to still have some HF present and a little bit of the H plus and the F minus ion. Okay, notice, obviously, once again, we have these little hydronium ions floating around, those H3O pluses, okay, and that corresponds to the H plus. And, of course, we have our F minus ions. In this situation, though, we also have HF still present. It's still hanging around, okay, and that's because the HF acid is weak. It doesn't ionize completely like we see over here with the strong example. So you're basically going to have 3 different species present. So what are some strong acids that you guys should definitely know? Okay, well, hydrochloric, nitric acid, sulfuric, and perchloric acid, these are extremely common. Okay, so go ahead and just memorize these, know them. I'm not going to be giving you the formulas always, so spend some time with this, just like we took some time to memorize. That ammonia, or NH3, is a weak base. You're going to do the same thing with these strong acids. Make sure that you're comfortable with these. Okay, notice, guys, that they have specific formats and formulas associated with them, just like any other compound. So make sure that you know both formula and name. Okay, so something else to kind of point out, you may have noticed this, acids can be basically mono, di, or triprotic, and really this mono, di, and triprotic is referring to how many protons each acid is capable of donating. So H2SO4, okay, or sulfuric acid, as you have now memorized, is a diprotic acid. So what does this mean? It means that it has 2 protons that it is capable of donating. So the first proton that it can donate is basically shown here, basically this ionization process. You get this proton and HSO4 minus ion. Okay, this initial production of these 2 ions is a very strong process. Okay, so this dissociation, sulfuric acid is very strong. Now, bisulfate, is not a strong acid, it's a weak acid. So this ionization process here is not going to be 100% like we see in this first process here. Okay, so basically what you need to understand is obviously there are acids that can be, giving away only 1 proton, 2 protons, or 3 protons, but understand that each successive proton that's given away is not necessarily going to be done so in the fashion of a strong acid. Okay, so as we see here, the first proton given away by sulfuric acid is a strong ionization, okay, because sulfuric acid is a strong acid. Okay, the bisulfite is sulfate, excuse me, is not a strong acid. It's in fact a weak acid, so the ionization is not going to be lying as far to the right as we saw in the previous step. Okay, so something else to understand is that in order to be a Bronsted-Lowry acid, you do have to have H atoms that can be transferred, right? Acids have to be able to give away those protons. They donate those protons. All right, but not all H atoms can be given up. Okay, so there's going to be molecules where, yeah, it has a hydrogen in the formula, but that hydrogen is not attached to an atom that allows it to be given away. So let's go ahead and let's look at an example. Okay, so acetic acid is as follows. Okay, so acetic acid is really a molecule that looks like this. Okay, so acetic acid is an example of a monoprotic acid. Now some of you might say, hey, well, it's monoprotic, but look, it has 4 hydrogens in the molecule. So how come it's only monoprotic? Okay, well, in this situation, what matters is what the hydrogen is attached to. Okay, so there's a large electronegativity difference between oxygen and hydrogen. Okay, so the electron density is pulled towards this oxygen molecule, where this hydrogen here is attached. Notice the hydrogens here, though, are attached to carbon, which has a pretty similar electronegativity to hydrogen. So these are being shared evenly. So really what happens here is that this is your only acidic proton. And the reason why is because it's attached to more electronegative elements, and basically the electron density is not being shared as evenly. Okay, so what ends up happening is we remove our protons here. Okay, so in this case, the only one that's going to be able to behave as an acidic proton is the one that's attached to an electronegative group. Okay, these three over here, there isn't a big electronegativity difference. It's not going to be susceptible to being removed. So you subsequently aren't going to see any more ionizations coming from acetic acid. So acetic acid is a monoprotic acid, even though it has 4 hydrogens attached to the molecule. Okay, so what things are attached to matter a lot with respect to if it's an acidic proton or not. Okay, so some more points to note, some acids that you guys need to be familiar with. So oxyacids, they're going to have an acidic proton attached to an oxygen atom. Okay, so phosphoric acid, acetic acid, okay, nitrous acid, hypochlorous acid. These are all examples of oxyacids. Now, organic acids are typically contain what's known as a carboxyl group. So acetic acid, okay, has this carboxyl group that we're talking about, and they are usually very, very weak. Okay, acetic acid is a weak acid. It doesn't ionize very much. Okay, now the other thing to notice is that hydrohalic acids, with the simple symbol HX, they're going to have acidic protons that are attached to halogens. So HCl, HBr, HI, yada, yada, yada. Okay, so all of those different types of acids are going to be attached to different things, though. But notice in each of these cases, we have hydrogen attached to some sort of electronegative element. So we've talked about water a little bit before. Now we've indicated that it's amphoteric and that it can act as an acid or a base. So something that we need to look a little more in depth at is that water will donate protons to other water molecules. So if I just have a glass of pure water hanging out, what you're actually going to have happening in that container is that one water molecule is going to behave as a base, one is going to behave as an acid, and one is going to behave as a base. So one's going to give away its protons, one is going to accept the protons. Okay, and that's going to give us the hydronium ion and the hydroxide ion. Okay, and so basically we get this process called autoionization. Basically these two water molecules, they interact, they give us this hydronium and this hydroxide. Now, if we write an equilibrium expression for this reaction, notice we have H3O plus, or that hydronium ion, and that hydroxide ion. Now, we've excluded the H2O, obviously, because we don't ever include pure liquids or solids in our equilibrium expressions. Okay, so now that we've written our equilibrium expression with respect to our autoionization process, let's go ahead and let's look at how we can utilize this expression. Now we can rewrite our equilibrium expression that we just saw on the previous slide with respect to Kw. Okay, so we call this the water ionization expression. And basically, the ion product constant, or the dissociation constant associated with water, is going to vary at specific temperatures. Okay, so at 25 degrees C in pure water, the Kw value, the constant, is going to be equal to 1.0 times 10 to the negative 14. So when you have a pH equal to 7 at 25 degrees C, we know that the concentration of our H3O plus, or H plus, and our OH minus is going to be 1.0 times 10 to the negative 7 molar respectively. Okay, so a neutral solution is going to have equal concentrations of H plus, or hydronium ion, and OH minus. Okay, an acidic solution is obviously going to have more H plus, or more hydronium ion. Okay, and a basic solution is obviously going to have more hydroxide ion than hydronium ion. Okay, and we can use this relationship right here to calculate concentrations of our hydroxide or hydronium ion, and subsequently figure out if we have an acidic, basic, or neutral solution. So we know that our constant at 60 degrees C here is 1.0 times 10 to the negative 13. So we want to know the concentration of H plus and OH minus for a neutral solution at this process. Okay, so we know that H plus times OH minus is going to give us that Kw value. Okay, notice this Kw value is at 60, so it's a little different than what we saw at 25 degrees C. Okay, but that's going to be equal to 1.0 times 10 to the negative 13th. Okay, and if we want to know the concentration of H plus and OH minus for this situation, okay, we know that for a neutral solution, the concentration of H plus and OH minus are going to be equal, right? So basically what we have is x times x is equal to 1.0 times 10 to the negative 13th, okay? Or we can look at this as x squared is equal to 1.0 times 10 to the negative 13th. And x is subsequently going to be equal to the square root of 1.0 times 10 to the negative 13th. And that's going to give us 3.16 times 10 to the negative 7 molar concentration. Okay, and that's going to be true for both our H plus and our OH minus. Okay, and you can obviously always plug that number back in to your equilibrium expression here. Okay, and that should subsequently give you your 1 times 10 to the negative 13th. Okay, so assuming the same conditions, okay, we've been told our concentration of OH minus is going to be 1.8 times 10 to the negative 9 molar. Okay, so what we're going to do with this is we're going to take our Kw value. We're assuming this is at 60 degrees C because the earlier portion of this problem indicates that. If not, you can go ahead and assume the Kw at 25 degrees C. So remember, this is our equilibrium expression. Okay, we know Kw, right? We know that it is 1.0 times 10 to the negative 13th. Okay, and we know that that's going to be equal to H plus. And we know our OH minus, because they gave it to us, so 1.8 times 10 to the negative 9 molar. Okay, so we go ahead and we divide out our 1.8 times 10 to the negative 9 molar to both sides. Okay, so our H plus is going to equal 1.0 times 10 to the negative 13th divided by 1.8 times 10 to the negative 9th. Okay, and this is going to give us 5.5 times 10 to the negative 5th. Okay, and that's going to be our concentration of H plus. So now another question that they could ask us is if this is an acidic or basic solution. And what we would do there is we would compare our concentration of OH minus versus our H plus. So we just calculated our H plus. We have our concentration of our OH minus. OH minus is 1.8 times 10 to the negative 9. Okay, our H plus is 5.5 times 10 to the negative 5th. Okay, the 5.5 times 10 to the negative 5th is a bigger number, so I have more H plus present. If I have more H plus present, that means that I am going to have an acidic solution. So Kw, basically that ion product constant is going to vary with temperature. Obviously, when we first saw it, we saw it at 25 degrees C. And basically we know that it's that 1.0 times 10 to the negative 14th. At other temperatures, you're going to have different values, as we saw in the specific problems here. Obviously, those would be given to you. The Kw at 25 degrees C, though, needs to be memorized. And you can use this expression to calculate the concentrations of your H plus and your OH minus. And you can subsequently use other these equations to calculate other information, such as the concentration of your H plus, the concentration of your OH minus, and the relative acidic or basic properties of the solution you're looking at. Okay, so now that we've looked at the strength of acids and bases, and we've looked at how the Kw equilibrium expression is useful, we're going to go ahead and look at a few other things.